I tried so hard and got so far, but in the end, it doesn't even matter. I had to fall to lose it all, but in the end, it doesn't even matter. I tried so hard and got so far, but in the end, it doesn't even matter. I had to fall to lose it all. And in the end, it doesn't even matter.
All right, folks, let's go ahead and pick things up about where we had left off last time we had met, which was our discussion of thinking about incorporating production into our general equilibrium analysis. So that's what we're going to wrap the course up with this evening. I will provide a little bit of time at the end of class as well to finish off those CAPE evaluations if you haven't had a chance to actually sit down and do that. But the agenda for the last segment of the course today is following up on our incorporation of production into the GE framework. We had concluded last class by at least graphically thinking about the derivation of the production possibilities frontier as the way of expressing the Pareto efficient set in an output orientation in what we call output space, as opposed to input space where we were looking at the isoquants. We're going to relate this back today to a pure exchange economy, which should again be kind of like a mind-blowing moment to some extent. And we will wrap up the course by defining a competitive equilibrium in the bigger scaled version of the model where we have two consumers, two producers producing two goods using two inputs. And that's where we will leave things. So I think we had wrapped up our last segment kind of looking at the Pareto efficient set in the input orientation here. And things looked very, very similar to what we were looking at when we were thinking about having outputs Y and X on the vertical and horizontal axis here. Notice this diagram is drawn in a way where capital is the vertical axis variable, labor is the horizontal axis variable. Okay, so I always draw this first from individual X's perspective, where the bottom left is the usual origin. We recognized that the condition that would identify the Pareto set, if we had these interior tangencies, implied that the marginal rates of technical substitution for the technologies had to be equal if we were allocating inputs efficiently in this framework. And we had derived the Pareto set in output space last time by thinking about different allocations along the Pareto efficient set in the right diagram, which was the input orientation. So we thought about what happens if we were at a point on the right diagram, like this bottom left point here, where Y gets everything, X doesn't get anything, which means that must correspond to the maximum amount of Y that could be produced in this economy. And then we thought about going ahead and moving up this Pareto set to other efficient allocations where we would be considering shifting resources away from sector Y towards sector X. And we saw that doing this required us to give up a little bit of Y output in order to produce more X. And we thought about doing this as we moved from left to right on the Pareto set, plotting the efficient point in input space, then plotting the efficient point in output space. And when we were done with this, after we had thought about, smoothly reallocating resources from the bottom left point of the Pareto set to the top right point in that Edgeworth box, what we've done here is we've actually wind up plotting a very familiar graphical tool, which is really probably where all of your Econ 1 started. And that was the PPF, the production possibilities frontier. So we are now able to think about this in a more complicated framework here, where we have multiple input usage in our technologies. We got multiple technologies, multiple products. And I think this is really the first time we've been looking at this output orientation on the left side of the screen like that, other than maybe some data we looked at in the first class. So we should be familiar with this idea that if we are dealing with an inefficient allocation, that's a combination of capital and labor that are not efficient, meaning with that capital and labor allocation, we could do something different to increase the outputs of both firms. That would put us somewhere in the interior of the production possibilities frontier. Okay, here's an inefficient allocation where we're doing a lot of Y production, but not a lot of X production. So that would show up over here. Okay, here's another inefficient allocation, right, off of the Pareto set where we're doing a lot of X production, but not much Y production, right? And we can think about mapping this out into the output space. So what I want us to be able to do is go through an example in a moment to think about how to derive the production possibilities frontier. And then furthermore, consider the set of points inside of the frontier, which defines the full production possibilities set. Okay, the production possibilities set is everything on the frontier and inside of the frontier, kind of like the technology set, if you will, but for a multiple output situation here. We know that points on the frontier itself are efficient because they were mapped from the Pareto efficient set in the Edgeworth box. So again, points inside or below, we know these were technologically inefficient points. And if we had any points that were outside or above the frontier, then those points were technologically infeasible, right? We could not produce things out there given the inputs and the technology we could apply to those inputs. So this should be, somewhat familiar of a discussion given everyone has this background from like Econ 1. You might remember the slope of the PPF was important, okay, with respect to things like thinking about gains from trade, with respect to things like input specialization. So we're going to come back to that notion in a moment. But what I would like to do first is to go through an example where we have these smooth Cobb-Douglas technologies, and we're going to derive a PPF, and we're going to think about how properties of the underlying technology may influence the shape of the PPF, of the production possibilities frontier, and as a consequence, the underlying production possibilities set, the interior and the boundary of that frontier. So we have here an endowment of capital and labor. Okay, meaning any efficient utilization of resources is going to use all of that capital and labor. Okay. And let's suppose we have each firm using a technology given by our standard Cobb-Douglas K to the alpha, L to the beta. I'm not going to plug in constants for alpha or beta yet. We'll be able to kind of think about the role that those things have on the production possibilities frontier once we derive it. So this is going to be a little algebraically involved for the moment. Notice the index J here is referring to which producer we're dealing with, the producer for good X or the producer for good Y. And our goal here is to derive an expression for the production possibilities frontier. Okay. So first thing we have to do to find the PPF is we need to figure out an expression for the Pareto efficient set with respect to the input orientation of the Edgeworth box. And we're going to recognize our ability to do that in this particular case where we have these smooth differentiable technologies is by using this necessary condition where the marginal rates of technical substitution are equal to each other. Hopefully this is not too much of a stretch that if we had to calculate the MRTSs, we're going to take the marginal product of capital divided by the marginal product of labor. and that would give us the MRTSs. And you'll notice a lot of stuff starts to cancel here. A lot of things cancel out. The alphas cancel from both sides of that equation, so do the betas. In fact, we should be able to kind of see that here, right? Alphas are going to cancel, betas are going to cancel. Hey, we can start combining terms in the numerators and denominators, right? This is going to leave us with a K in the bottom, an L in the top. Okay, here we're going to have again a KY in the bottom, an LY in the top. And then I think in my next slide, I actually take the reciprocal of all that. So we got KX over LX equals KY over LY is implied by that tangency condition. And then hopefully you remember how we found the Pareto efficient set when we were dealing with the pure exchange economy, right? Looks like we have 4 variables here, but we know KX and KY are related to each other through what? These things are related. These things are related. What relates them? Good. It's the endowment through the resource constraint. Right? K bar is the total amount of capital. So another way we could write KY, that's just K bar minus KX, just like LY can be written as L bar minus LX. And then we can cross multiply, simplify, and we should wind up with the following. Okay, this is the expression for the Pareto efficient set of allocations. That's what we're looking at right here. And you might have done enough problems to recognize this feature, but if the technologies are identical, okay, or if the preferences are identical, the Pareto set winds up being the diagonal of the Edgeworth box when we have these nice smooth continuous preferences. And that's exactly what that expression in the yellow box is, right? Think about it. The box is L is the base, K bar is the height, right? So KX equals, right, the height of the box, the rise over the run of the box times the x-axis variable, which is labor. So that equation in the yellow box there, that is literally the diagonal from the bottom left to the top right of that Edgeworth box. Now, first thing we did here is we found the Pareto efficient set of allocations in input space. Okay, in input space. What we need to do here is we need to rewrite this in a way where we've gotten rid of the inputs and instead we have the outputs. And the way we're going to do that is by using the production function and plugging in the Pareto efficient set. So here is our Pareto efficient set. What we're going to do is we're going to take that and we're going to plug it in. So now we're not just going to be looking at any particular combination of things that firm X could produce. We're going to be looking at the efficient allocations that firm X could produce. Okay, so we plug that in there. And you'll notice now what we'll be able to do here. We have an X on the left side of the equation. We have LX on the right side of the equation. In fact, we have 2 of them, so we'll combine those bases together in a moment. Maybe not too hard to see what is going to happen because we have this alpha exponent here, right? So if we combine the purple bases, then we wind up with this nice and tidy L sub X to the alpha plus beta. And what this is going to do is it's going to let us in some regards invert the technology. That's what we're doing. We're inverting the technology after we plugged in the efficient value of capital. Okay, so all we have to do here is I'm going to solve for LX. Okay, I'm going to solve for LX. Okay. If you're wondering why didn't you solve for KX? Well, we did that first. Okay, we did that first already in the bottom right. That was the expression for that Pareto efficient set. There it is, PE set. Okay, what I'm going to do now is I'm going to plug this in to the Pareto efficient set. And you'll notice what we've done is we've written L as a function of the output. X is how much output the firm is producing. Okay. What substituting Ln over here is going to do, it's going to allow us to figure out how the efficient level of capital depends on X, the level of output. Okay, so that's all we're going to do. I'm going to plug in LX right over here. And the result of this is going to give us K as a function of X. Right now, the other thing we can do here is if we want to, and I'm going to do this in a moment, we can bring back firm Y's variables, right? KX is just K bar minus KY, right? LX is just L bar minus LY. So another way of describing the efficient set, which is equally valid, it would be from a firm Y's perspective in the input orientation. This is both describing the diagonal of the box from the bottom left to the top right. Okay, same efficient set. All right, so if we wanted to think about deriving L sub Y as a function of how much Y is produced, we could do that here as well. Okay, so I just want to be clear, what we've done is we figured out how much does the labor that X uses on the efficient set, how does that depend on how much output X is producing? So we're going to figure out the same thing for firm Y's labor. And then what we'll be able to do is relate LX and LY through the labor constraints on resources. So we have LX as a function of X. We're going to get LY as a function of Y. And then we're going to plug them into the resource constraint. That's going to give me a relationship between X and Y when we're using all the resources with the Pareto efficient set plugged in. Okay, which should correspond to the definition of our production possibilities frontier. So yeah, so X is the amount produced. So what we're looking at in the bottom left here in that purple box, Dylan, that is the amount of labor LX required if we're efficiently producing a particular level of X. I hope that makes sense. That's exactly what that thing is telling us there. Okay, so I want to find the same thing, but for the labor required for firm Y to produce a particular amount of Y. Okay, so by pretty much the same logic here, we're going to take the efficient KY, we'll plug that in. Okay, we'll get the same base on our L, and then we can invert the left and the right side to solve for LY as a function of Y. And now in the bottom here, we have the labor Y needs to use along the efficient set of allocations as a function of how much Y they are producing. Okay, so at this point, we have both input demands. Okay, these are the input demands for labor, okay, conditional on the level of output, X and Y. In order to generate the PPF, all we're going to do is plug these into the resource constraint for labor. And you know, I have this note here, it says, alternatively, you could have used the constraint for capital. We could have. We've done everything here where we solve for L's. We could have gotten K's instead if we wanted and plugged them into the capital resource constraint. You'll get the same production possibilities frontier. And I encourage you to verify that on your own. Okay, so the market clearing condition for the labor market. It was that the total labor demanded by the firms, LX plus LY, had to equal L bar. This was really the resource constraint. And now we can go ahead and substitute both values that we have for the demand for labor for X and the demand for labor for Y. And I'm going to argue what we have found here is the equation of the production possibilities frontier. It's a little ugly. In fact, what I'm going to recommend we do is let's divide through by this constant that's out front. See, that's the same in both. We could factor that out, divide through by it. Okay. And if you do that, this leaves us with the following. It leaves us with the following expression. And you can sort of check, there's some careful math with the exponents here to wind up in this form. But at this point, the important thing to note here is this is a cleaned up equation for the PPF. It's not in Y equals form. We could get it in Y equals form. That may help in certain situations to see the shape of it better. Okay, but I'm going to leave it in the form we have it here now. We should see that what we have is some relationship between X and Y. And everything on the right-hand side of that equation is a what? Like K bar, alpha, beta. Those are all what? Yeah, they're all constants. That's right. So I'm going to just say here, generally, the form of our PPF looks like the following. And, you know, if you're like, hey, why didn't you just pick numbers for alpha and beta? That would have made our lives a little easier with some of that algebra. I agree. But I want us to be able to see how the shape of the PPF depends on those production parameters, right? We know alpha is that elasticity of output with respect to capital. Beta is the elasticity of output with respect to labor. And those things will have an effect on the production possibilities frontier. So that is why I've left them there. Okay, now we're going to start off by looking at, I think, the easy case here. Okay, suppose alpha plus beta equaled 1. I'm not going to worry about the individual values, but suppose the sum of those exponents add up to 1. Does anyone remember what the technological implication of that was from way early on in the course? It's actually not a linear tech, right? If you think about the production function, it's not necessarily a linear tech, but it is related to returns to scale, Elise. You're on it. Yeah. Hi, Zhao, I like what you're saying. Yeah, if alpha plus beta was equal to 1, that meant we had a constant returns to scale Cobb-Douglas technology. Okay, and I already see a couple folks in the chat are very astute. They're like, hey, that means if we plug in 1 for alpha plus beta, what type of function does the PPF become if alpha plus beta is 1? Think about the exponents on X and Y. What happens to it? So if you plug in a 1 for alpha plus beta, I want to know what happens to the equation in the yellow circle. What must it look like? Yeah, you're on fire, Elise. Yep, Keegan, I like what you're saying. So if the exponents on X and Y are 1, what type of equation would you be graphing? It's got to look like a what? Yeah, gotta be a straight line. Absolutely. It is a downward sloping straight line. Okay, so if the technologies are constant returns to scale. You actually wind up getting a linear production possibilities frontier here. Okay, meaning as you move along the production possibilities frontier, the rate at which you give up Y to shift production to the X sector stays constant. Right? If you have a linear PPF, every unit of X requires you to give up the same opportunity cost in terms of the Y that is foregone. Okay. This is one case that we could think about here. Now you can probably see where we're going with this. If alpha plus beta added up to a number that was less than 1, what was the technological implication of that? Anyone remember? Yeah, Jordan, yep. On it. That means we got diminishing returns to scale. Right? Or decreasing returns to scale. You can call it either way. Diminishing returns, decreasing returns. And if alpha plus beta is less than 1, like let's suppose for a moment that alpha plus beta added up to a half. And we plugged 1/2 in for those exponents. Then the equation wouldn't be X plus Y equals a constant anymore. It would be what? We plugged in a half for alpha plus beta. What did the exponents become in that case? Yeah, both squared, right? You get X squared plus Y squared equals a constant. Anybody remember what shape that is from your maybe your calculus class, algebra, geometry class? X squared plus Y squared equals some constant. Yeah, it's a circle. It's absolutely a circle. Okay, if you have coefficients on X and Y, it can distort the circle into an ellipse. But here's my point. If alpha plus beta, if they're positive, but their sum is smaller than 1, then we're going to get some sort of diminishing returns to scale technologies. But what that means is the production possibilities frontier will actually be bowed outwards, implying that we would have a strictly convex technology set. The area inside is a strictly convex set. Okay. That'll be important in a moment when we think about profit maximization, but I'm going to come back to that idea. All right. Now, the other case that we could have wound up with is maybe the technologies exhibited increasing returns to scale. And by the way, if the PPF bows outward, anybody remember what was true about the opportunity cost in that case of producing more X? This was definitely something you talked about in Econ 1. Yeah, the opportunity cost is going up. That's right. It's increasing. As you produce more X, you have to give up more and more and more Y. Okay, that was related to input specialization, right? Every unit was not equally as productive because the marginal productivity of units changed along the technology. All right, now last case, if alpha plus beta is greater than 1, like if they were 2, and you plug in a value of 2 for alpha plus beta. Okay, then you would get like X to the 1/2 plus Y to the 1/2 equals a constant. Anyone want to take a wild guess at what happens to the production possibilities frontier in that case? Yeah, it'll be bowed inwards. That's right. And you'll wind up getting a non-convex production possibility set. This area inside of the purple region, that's non-convex, is that right? You can pick 2 points in that yellow region, you can connect them with a line, and it's possible to choose those points in a way where that line will fall outside of that set. Okay, so we can sort of see here again, alpha plus beta, right? The returns to scale properties related, right, to the way the opportunity cost changes along the production possibilities frontier. Okay. You can probably imagine what happens if like maybe the Y sector had diminishing returns, but the X sector had increasing returns. Then you might get one that kind of curvy. It's bowed outwards at one point, but then it's bowed inwards at the other. You know, that can happen. What I'd like to do here at this point is summarize the steps we took to derive the PPF in this framework. Okay, the first thing we did is we found the Pareto efficient set in the input orientation in the Edgeworth box. Okay, once we had that Pareto efficient set, we substituted this into the firm's production function and inverted it to figure out the input requirement along the efficient set. And in this example, I did this for the labor input requirement, but we could have just as easily done it in terms of capital. The third thing we did is we substituted the input requirements for each firm into the market clearing condition for that input. Again, in this example, I got rid of capital and we used labor. We used the labor resource constraint. But if you had done it the other way by eliminating labor using capital and then use the capital resource constraint, you would wind up with exactly the same PPF. So you have a little bit of leeway there. Okay, do I want to do things in terms of labor requirement, the labor constraint, or capital requirement? The capital constraint. So you'll probably have to do this on the quiz. In fact, I'm giving you a big hint that I mentioned in the last segment, but the last problem on the last problem set, I think it's the one where you have to derive a PPF. That'll be very useful for you to understand for the quiz. Okay, so we've gone through, we thought about graphically deriving the PPF, and now we've seen a numerical example of how to do this by invoking some calculus tools and some reasonable logic regarding the efficient set. We also kind of recognized a moment ago, looking at as we change the returns to scale, it caused the shape of the PPF to change in a way that affected the nature of opportunity cost between the two goods. In that, right, we're producing more of one good along the efficient set requires reducing some of the other good as a consequence of the resources already being used efficiently. We can't just get more of something without having to give something up. And we can quantify this trade-off. Right? We think about that as measured by the slope of the PPF at a particular allocation. Now, I want you to think about the following. What is true about the cost of every allocation along the production possibilities frontier? In fact, this is true about every allocation in the production set. You to think about that. If I'm on the frontier, how much capital and labor are we using? If we're along the frontier, how much capital and labor is being used? Yeah, Hai Zhao, you nailed it. All of it, right? We're using the whole Edgeworth box. Okay. So just think about that, right? At this point, we're using all of it. At this point, we're using the full K bar, L bar. Here we are. Even inside, we are just inefficiently. We're somewhere in the Edgeworth box. Okay, which means the total cost of production anywhere in that production possibility set. Let's think about that. If the prices of capital and labor are constant, the amount of capital and labor we're using anywhere in the PPF or in the inefficient part of it also are constant, then what has to be true about our cost at any point on the boundary or on the interior of the PPF? Yeah, Winnie, you're true. Yeah, that's it. The cost is the same. That's right. So if we move along the PPF, the total cost to the firms doesn't change. Okay. We're using still the full amount of capital, the full amount of labor, and the prices of capital and labor are constant. All right. So if I move, between, these two efficient points, okay, the total cost is the same. I'm still using all my capital and all my labor. Okay. So I'm going to argue that at any allocation along the frontier, right, regardless of how much X and Y we're producing, the cost of producing a particular combination of X and Y is actually constant. Okay. We can cut back on X, produce more Y. We give up some cost of producing X, but we add on some cost of producing Y, and those things will offset each other because we're still using the same total amount of input. Now, what we're going to do here is we're going to think about totally differentiating the expression for the total cost of production. Okay, and I'm going to do this in a way where we're going to try to isolate the slope of the PPF. Right, the slope of the PPF is dy dx. Okay, so what we're going to do here is we're going to totally differentiate both sides. So the left side, dc, but the right side's a constant. So when we totally differentiate the right side is going to be what? Yeah, going to be 0. Okay, and dc, right, the differential of the left-hand side, how can the left-hand side change? Well, it can change because we changed X. It could change because we changed Y, or it could change because we changed both. Okay, the term in the green here is how much the cost changes when we change X by a little. Then we multiply it by how much we actually changed X. That's the total change in the cost from changing X. Okay, the term in the blue here is the change in the cost from changing Y a little bit. And then we multiply that by how much we actually change Y. That's the total change in the cost from changing Y. So if I add the green term and the blue term together, that must give me the total effect on how the cost changes. And if we move along the production possibilities frontier, we said the total change has to add up to 0 because the cost does not change. Now, the terms in the square boxes in colors, what are those? In the square boxes, I want you to think carefully about what those are. Yes, very good. I see folks are saying in the chat, well, that's the partial derivative of a cost function with respect to output. You're right. It's the marginal cost. The term in the green box is the marginal cost of producing X. The term in the blue box is the marginal cost of producing Y. Okay, so we can rewrite this expression here a little bit, given that those partial derivatives are familiar to us. Now, our goal is to find an expression for the slope of the PPF, which means we want to isolate dy over dx. So let's move all the terms multiplied by dx to the right. And then we'll divide through by mcy, and that'll leave us, or sorry, rather, let's divide everything through by dx. And then we can subtract mcx to the right, divide through by mcy. And you wind up finding here what is called the marginal rate of transformation. This is a fancier word for the slope of the PPF. This is sometimes called the marginal rate of transformation or the marginal rate of commodity transformation. I'm going to just refer to it here as the MRT. But the MRT is the negative ratio of the marginal cost of production. Okay, so the slope of the PPF is given to us by the ratio of the marginal costs of producing X relative to Y. And this measure here, the marginal rate of commodity transformation, that is exactly the measurement of opportunity cost that you had learned way back in Econ 1. Okay, and in this case of this particular picture, right, where we have a strictly convex production possibility set, okay, then moving along the PPF will result in a diminishing, sorry, not a diminish, I want to say an increasing opportunity cost, right? The absolute value of the slope is getting bigger. You're like, technically the slope becomes more negative, but it's not really diminishing. It's saying you have to give up even more Y as you produce more X, not less. All right, now, how does a society decide where they want to produce on the production possibilities frontier, right? Which allocation should we choose? And the answer to that really has to do with the firms. Okay, which point will the firms decide to choose? How much Y will they produce versus X, given that there's a resource constraint between shifting production to Y and X? And the answer to this has to do with profit maximization. And given that the cost of any allocation on the PPF is the same, I'm going to argue that the profit maximizing allocation for the firms must involve just generating the most possible revenue across goods X and Y. And so I'm going to argue here that maximizing revenue, that must correspond to maximizing profit, given that the cost of any allocation along the PPF is constant. Now, total revenue, I think should be pretty straightforward to compute here, right? It's going to be PX times X plus PY times Y. And what we're going to do here is we're going to think about plotting a revenue indifference curve in this space. And hopefully you can think about seeing where we're going to go with this. If I imagine plotting all the combinations of X and Y that yielded me the same revenue, okay, like let's fix the level of total revenue and plot all the combinations of goods X and Y. First off, if we were to plot this equation where we have some constant equals PX plus X plus PY times Y, what shape must that equation have when we graph it? It looks just like a budget constraint, right? Yeah, it's going to be a straight line. Absolutely. And the slope of that straight line should be very, very familiar. Okay. Now, the vertical intercept. In fact, let me just move this to the top of the screen. The vertical intercept, if we plotted this equation, okay, I'm going to refer to this as an ISO revenue curve. ISO means equal, right? We've had ISO cost lines before. We talked about ISO profit lines before, ISO profit curves. This is an ISO revenue curve. Any two allocations on this curve yield equal revenue in total across the producers, across these sectors. Okay, and the slope of that thing is negative PX over PY. The y-axis intercept, though, is the total revenue divided by PY, which means if total revenue was to increase, if we wanted to look at a different combination of X and Y that yielded us a different level of revenue, a higher level of revenue, what does that imply will happen to the ISO revenue curve, given that the slope doesn't change when you change the level of revenue? The question is, if we increase TR bar, what's going to happen to the blue line? Yeah, that's right. We're going to get a parallel shift up. That's exactly correct. Meaning higher ISO revenue curves must correspond to higher levels of revenue. Given that the cost is constant anywhere in the production possibility set, higher levels of revenue must correspond to higher levels of profit. Okay. So we can formalize a profit maximizing allocation here as follows, right? Which point on the PPF should society choose? Well, they're going to choose the point that maximizes profit, that puts them on the highest possible ISO revenue curve, meaning the optimal solution here is going to be characterized by what type of condition? Yeah, tangency condition, absolutely. Okay, so I'm going to argue that that is the profit maximizing combination of X and Y for this society. Okay, now, what is the tangency condition that is consistent with profit maximization? Well, we know the slope of the PPF was equal to the ratio of the marginal costs, and we had a negative sign in the front, it's downward sloping. Slope of that ISO revenue line is negative PX over PY. So if we're indeed at that profit maximizing allocation across the whole economy, I'm going to argue that this is absolutely consistent with each of the individual firms maximizing profit. Right? Like if firm X maximized profit, it's going to produce until PX equals the marginal cost of producing X, until price equals marginal cost. Same thing with firm Y, which is not too surprising to see that the tangency condition involves really both of those things being true simultaneously, right? If PX equals MCX and PY equals MCY, that condition will hold. Okay, so note the FOCs of the individual firms were given by price equals marginal cost. So if you took those two FOCs and divided them by each other, that's exactly the tangency condition that we are looking at here. Hey, the tangency condition is just the ratio of the individual firm's profit maximizing conditions. Okay, so if the firms are maxing profit and those FOCs hold, this will be the allocation that will be chosen. Now, another big picture moment here, I hope. But I want to relate this back to the pure exchange economy. You remember the pure exchange economy? We didn't have any production. And there was no technologies to worry about here. We didn't have to talk about profit maximization, no cost to firms to think about. In fact, in that pure exchange economy, the amount of X and Y wasn't determined by the firms. It was just what? Yeah, it was just given. It was endowed. Like Y star was just, we called it Y bar, right? And we abstracted away from this whole discussion. X star, we called X bar. That was it. But now the story is a little bit richer than that. The prices in the market guide us to the efficient profit maximizing allocation of X and Y, right? So that's what's determining the firm's production levels here. And given the quantity of each good supplied, okay, we should be able to think about the Edgeworth box from the perspective of the consumers now. Right? If the firms had picked a different point on the PPF, then from the consumer's perspective, there's a different Edgeworth box they're interacting with. Okay, so this is really the essence of thinking about the full scope of the GE framework. We got the firms maximizing profit on one end. We got these consumers trying to maximize their utility at the same time. We're trying to figure out the ratio of the prices of not only the outputs, but the inputs as well, that clear all of the markets simultaneously. Okay, so this is, the big picture here in terms of the general equilibrium framework that should hopefully tie back what we did in the pure exchange economy framework with what we've done now, thinking about incorporating production. The next step would be to do what we're going to do next in this next slide, but I will not have you solve for a full competitive equilibrium in this model, where we have two sectors, two consumers, and two inputs. Okay, but if we wanted to define a competitive equilibrium, here's how we would have to do it. Remember, a competitive equilibrium has two components. There's an allocation, and then there's a set of price ratios. And you'll notice the way I've drawn this, what good have I normalized every price against? Yeah, we're treating good Y like a numeraire commodity, right? We can measure the price of everything relative to good Y. It doesn't matter which price you choose to normalize against. So we're dealing with two elements here, right? We have an allocation and we have a set of prices. Okay, such that, and I think this should be, sorry, there's a very small typo here, and I'm going to just identify it. Instead of X bar and Y bar here, it should be L bar and K bar. Right, we're not endowed with X and Y in this model, so there's a very small typo. Should be L bar and K bar there. But again, moving forward here, the definition of the competitive equilibrium involves an allocation and a set of prices, such that taking the prices as fixed, each consumer solves their utility max problem subject to their budget constraint. Second condition, taking the prices fixed, each firm X and Y maximizes their profits. Okay, they figure out what's the profit maximizing combination of output and input usage, subject to, of course, their technological constraints. So this condition was new compared to the last time we defined a CE for the pure exchange economy. Okay, so two things are happening. Buyers are doing the best they can. Sellers are doing the best they can, right? Individually, selfishly motivated buyers and sellers. Buyers are utility maximizing. Sellers are profit maximizing. The last thing that needs to happen for this to be a competitive equilibrium allocation is all of the markets must clear. Okay, so that the excess demand in any market, whether it's outputs or inputs, has to be zero. And exploiting the Walras law, if we have a situation with four markets, we only have to deal with how many of them to guarantee they all clear. Yeah, three of them. Right, there's three prices that we have to solve for here, three price ratios. So you're going to have three excess demands that you set equal to zero to give you a system of three equations with those three unknowns. Okay, so if you solve that resulting system for those prices, given the utility maximizing demands and the profit maximizing supplies, then you can find the equilibrium even in the bigger version of this model. Okay, now I mentioned that modern research has really gone so far, and you're dealing with, computational models with, infinite agents in some cases, thousands of agents, continuum of agents, whether or not they're consumers, producers, or both. So this is about where I wanted to wrap things up for the course here after defining the competitive equilibrium for this two-sector production model. You again won't have to solve for the competitive equilibrium, but you should definitely know how to derive a PPF. Okay, I think you should still know how to do your market clearing conditions, these sorts of things, but you will not have to do a full competitive equilibrium solution on the quiz. With that being said, this is where we're going to kind of wrap up the course material tonight. So we have a little bit of extra time left. What I would greatly appreciate from you all, if you have not already, I know you got maybe a couple email reminders, at least 2 email reminders at this point. But first off, this is not an easy class that you all are taking. We're aware of that, and taking it during a global pandemic, during a remote learning environment, is definitely a hard sell. If there's any year you could have taken a gap year, this would maybe not have been a bad choice. So you should definitely commend yourself for making it through the course, regardless of your exact quality performance. That being said, I hope you have all, really enjoyed the course as much as I have teaching it. So if you haven't already, please take the last few minutes of class today to go ahead, maybe even right now, I have the URL on the screen. Pull up the CAPE eval. Please provide myself and your TA some feedback. Your feedback is really critical for making sure we maintain high standards of academic achievement here at UCSD. If you've already given us that feedback, thank you so much in advance. It's greatly appreciated. A couple of last minute questions here. Other practice problems aside from the slides and PS5. Yes, you got lecture review problems. You got 10 of them. That should also help you do this. But my big hint, make sure you know definitely the PPF problem in PS5 should be very, very helpful for you on the quiz. Very similar. With that being said, I would also like to give a shout out to our UIA, Uday, who's been hanging out in lecture, taking questions on the periphery of the course. Thank you so much for being here. I greatly appreciate it. I know everybody else does as well.